Thanks a lot to Julia. Thanks a lot to all the organizers of these amazing webinars, and which have reached so much accolade around the world, and to all those who are present now, and to Daryl, of course, my best greetings. So today I'd like to talk about some long and painful work. So sometimes when you do research, you have an idea and you develop it rapidly and you get a cool, nice result. Sometimes it's a painful process. So today I'm going to talk about the pain, but the pain has been extremely pleasant in some sense. So today, just like Daryl presented this synergy grant, I just will briefly introduce you all to the newly established, in fact, the Center for the Mathematics of Planet Earth. So we have been active since 2.5 years, but we are, in fact, starting officially our activities as International Interdisciplinary Research Center of the University of Reading on August 1st, so next week, in fact. And this center brings together a lot of different people across mathematics, meteorology, earth science in general, and in fact other people from biology and economics and agricultural studies are being involved. So this is we have a new website, and I strongly invite you to give a look, and please give me feedbacks. It's still a work in progress, and we have been active in a lot of, especially in two directions. So in three directions. So having a visitor program, organizing activities of training and dissemination, including, just to mention one, last summer's London Mathematical Society School on Mathematics of Climate, where one of the speakers was indeed Daryl. And together with summer schools, there are lots of conferences and sessions at international conferences and workshops and other smaller events. Of course, another line of work is the preparation of research proposals. So today, as I said, I will talk a bit about some painful work. So the painful work comes from a lot of, from things I've been working on since I started my work in geosciences. So one of the classic problem of atmospheric dynamics. So the problem of understanding the so-called low frequency variability of the atmosphere, and I will of course go a bit more into detail. So we will try. So one of the main features of low frequency variability of the atmosphere are blocking events. Blocking events are persistent weather patterns that define special weather conditions on large scale. So the three questions we will try to address are the following. First, are these special conditions of the atmospheres coming with blocking events characterized by higher or lower instability than average? Second, is there anything special about the onset and the decay of these weather patterns? And third, is there something special at all about these weather patterns, or are they just sort of big fluctuations, or is there something truly unique about them? And at the end, there will be at the end of the pain, there was some unexpected gain, so some surprise bonus idea and result we got that I will share with you, of course. So some references. So this is a pretty, I will call it a gargantuan paper that is coming out on Reviews of Modern Physics with Michael Gill, 80-page, almost a book, in fact, on the physics of climate variability and climate change. Contains a lot of information on the mathematics and physics of climate, including the discussion of low frequency variability of the atmosphere, and then two more topical papers. One that came out this year with Andrei Gritsun, which has taken more than 2 years to about 2 years of work, and this contains most of the research contents that I will discuss today, and an earlier paper written with my former PhD student Sebastian Schubert, where that somehow was the starting point for this investigation. Now, the setting, physical-mathematical setting, physical-mathematical lens through which we look at climate is the one of a non-equilibrium system. So the climate is a non-equilibrium system, and all of its basically dynamical processes are driven by the presence of a non-homogeneous absorption of solar radiation, as radiation is prevalently and predominantly absorbed at near surface and in the low latitudes. And basically the entirety of the atmospheric and oceanic motions, small scale as well as large scales, result from the presence of such inhomogeneity in the absorption of solar radiation. And the presence of inhomogeneity of this in the absorption of solar radiation creates temperature gradients. Such temperature gradients are associated with the presence of available potential energy, and the conversion between such available potential energy into kinetic energy and the eventual dissipation of this kinetic energy and the diffusion of the available potential energy constitute the so-called Lorentz energy cycle, which is sort of a macroscopic concept, object that defines how the atmosphere and the climate system as a whole work. And few words we have already heard in the previous presentation, baroclinic and barotropic conversion processes are related to exchange of energy. Now, the nice thing is that the circulation and the atmospheric dynamics that results from such temperature gradient tend to reduce the temperature gradient themselves, thus leading the system so thus providing a global negative feedback to the system. And the climate as a whole can be seen as a non-ideal engine, and one can construct a thermodynamic equivalent of the climate system, which entails production of mechanical work and dissipation and irreversible heat transport. So the dynamics of climate, I've just given you a sort of ultra coarse-grained vision, relies on these large-scale budgets of energy and these entropy budgets. On the other side, the phenomenology of the geophysical fluids manifests itself in an incredible variety of variance. That is, variability is present in a huge range of temporal and spatial scales. And as well known, the detailed understanding and detailed analytical description of such motions depend strongly on the temperature in the spatial scales of reference. So of course we have fundamental equations, but in order to really use them, we need to take approximate balances and expand asymptotically such equations to create approximate equations that are useful for the range of interest. So today we're going to talk about the range of interest of synoptic and planetary waves and the temporal scales of 1 day and longer. So the quasi-geostrophic approximation is the approximation of interest for us. So two main phenomenologies occur in the atmosphere on these scales. So the synoptic variability is associated to mid-latitude cyclones, and this is responsible for day-to-day weather variability. And the planetary scale variability, as the name suggests, is associated with larger scale objects, and these are objects that persist longer times. So the main way to visualize this planetary scale variability, the main feature of such variability, is the so-called, what was in the 40s and 50s called the breakdown of zonal, the breakdown of the westerlies. So basically, typically we have in the mid-latitudes a strong prevailing westerlies in the mid-atmosphere, and such jet, which is of course responsible for the reason why it's faster to go by plane from New York to London rather than from London to New York, is disrupted when such large-scale persistent features are present. The understanding of this can be said as being one of the longest-lasting and still open problem of dynamical meteorology. Okay, something that has been obsessing dynamical meteorology since the very start of the field. So now, today we focus on probably the major manifestation of frequency variability in the mid-latitudes, the so-called blockings. So blockings are basically, you can see them as large-scale standing waves. So these are strong deviations from the zonal flow that persist in a geographically almost fixed position for several days. So there are two main sort of topologically different ways of through which in which such blocking occur. One is the so-called omega blocking, and because you see the isolines of the geopotential line arrange themselves in a way that resemble the capital Greek letter omega, and as you see on the left, on the eastern side, on the western side of the anomaly, you get northward advection. On the west side of the anomaly, you get southerly advection. And the other typical pattern is the so-called diffluent or dipole block, whereby we have a different topological configuration in the isolines, and we have a clear dipole in feature. So what is important in terms, one could, these things look interesting, but why are they relevant in terms of weather impacts? Because since these weather features are persistent in time, they can create long-lasting and sometimes hazardous weather condition. As an example, you could have a heat wave associated to a very long-lasting southerly advection. You could have flood condition. You could have persistent flooding. You could have basically large deviations from the typical local weather conditions. Sometimes these conditions are interlocked, and different regions, as an example, on the east and western side of the blocking, experience at the same time extreme and persistent anomalies with respect to the usual conditions. So blocks differ in terms of their topology of the isolines, differ in terms of the position. Blocking events typically occur either in the so-called Atlantic sector, so these are called Euro-Atlantic blocking, or in the Pacific sector. So this is near Bering Strait, or as I said, these are all large objects, and this is called the Pacific block. On the other side, sometimes we have blocking events that occur at the same time in the Pacific and in the Atlantic sector. So these are called global blocks. There is clear, let's say that these objects are visually very clear. I mean, there is clearly something very strange when these weather patterns are present, but they're very diverse. So it's a bit about Rorschach figures. Each person can see something different there. Is it possible to make a sense of such a huge variety in terms of phenomenology? And so this is the difficulty in understanding, in creating a theory. This is why people have struggled so hard in this direction. So a classical approach to first understanding blocking events goes in this direction. One writes a simplified equation that's relevant for the mid-latitude, as an example, a barotropic vorticity equation, and then one tries to find two kinds of stationary solution. So one hopes to find multi-stability in such a system, and one of the solution is one would like to be associated with zonal flow, and the other one should be associated with this strong anomaly from the zonal flow, which we name block. So in looking at weather maps, we would like solution A to look like the picture on the left-hand side, and we would like solution B for the same parameters looking like the solution on the right-hand side. Of course, solution A is prevalent, so we are typically in zonal flow condition, but sometimes, rarely, but not so rarely, so blocking occur regularly in the mid-latitudes, we would like to be in state B. So do we find such solution? Indeed, especially in the 80s, there was a huge effort in trying to associate a stationary solution to barotropic or even baroclinic quasi-geostrophic potential vorticity equations to such a solution. So I'm showing here the so-called modons. So these are stationary solution to the quasi-geostrophic potential vorticity equation. On the right-hand side is one of such a solution that looks a lot, visually at least, like an actual dipole blocking you see on the left-hand side. So the overall idea, I mean, there was a sort of a wide range of approaches and methodologies to studying this class of problem, but the overall idea was, okay, we can see in a coarse-grained sense the dynamics of mid-latitude weather as characterized by the presence of two or more weather regimes. So in particular, the zonal flow and the block flow. And the synoptic variability that I mentioned before acts in some sense as noise that facilitates the transition between these regimes, which live on longer time scales and larger spatial scales. So an interesting breakthrough in the understanding of these features came from the observation that the multi-stability is observed not just in the highly complex domain of the real atmosphere, but even in incredibly simpler settings, like a rotating tank. So if one has a rotating, basically in a series of experiments, especially coming from the group of Aris Sweeney, they discovered that in a rotating tank with some bathymetry or orography, depends how you want to see it, for the given value of the parameters, one could obtain multi-stability. There was coexistence of a blocked state and a zonal state. So the mechanism for the formation of blocking is relatively simple, even if its consequences are clear even in our highly complex and complicated atmosphere. So another sort of mathematically elegant, yet of course, simplified way to look at the problem was, and quite successful one, was the following. One can identify whether at a given day, the weather, the atmosphere is one of these weather patterns to be defined, and then study the probability of transitions from one weather pattern to the other using a simple Markov chain model. And as simple as it sounds, this line of work has been extremely successful. So there seems to be some sort of Markovianity in the coarse-grained dynamics. And these methods are also being used to construct basically post-processing of data. A problem is defining the optimal pattern, optimal number of patterns and identifying these patterns, but this is a separate problem. But anyway, the idea is we see Markovianity in the coarse-grained dynamics of the atmosphere of the mid-latitudes. Okay, these blocking are interesting. I'm trying to convince you these blockings are interesting. I've tried to convince you this blocking has a lot of impacts and they can be treated in some sort of nice, cool ways through mathematics. But what are the challenges? The challenges are that the two main challenges are that first, numerical weather prediction model, despite of course the incredible increase in the ability of state-of-the-art numerical weather prediction system in predicting the evolution of the weather, still have comparably hard time in predicting the onset and the decay of blockings. Whereas once we are in a block state, the weather forecast is quite successful because the system tends to follow persistence. Similarly, the performance of climate model has not improved so much in the last 20, 30 years, despite the incredible improvement of climate modeling as a whole. And still the IPCC class of climate models differ substantially in the statistics of blocking, and there is a huge uncertainty on how blockings will change. The statistics of blocking will change in the context of climate change. So the message is representing the prediction of blockings and the statistical representation of blocking is surprisingly difficult. So that's on the other side. Blockings, as we've seen, seem not to depend on, seem to be present also in much simpler setting than in our atmosphere and our climate system. So there is something fundamental that seems to be, that needs to be understood, okay? So this is the background. Now I'll try to tell you what we have been doing to at least try to shed some light on this. So the first problem we have tried to address is the understanding on how of the instability of the atmosphere in regular conditions versus in conditions when a blocking occurs. So if you want to study the instability of a system, let's say the typical, let's say I would say a very safe set of mathematical technology to adopt is the one based on Lyapunov exponents. So the Lyapunov exponents describe the asymptotic rate of divergence or convergence of infinitesimal perturbations around a reference trajectory. Okay, so the idea is to study the property of the tangent space of a dynamical system and construct basically and associate to the n degrees of freedom of the system n numbers that describe rates of divergence and convergence of nearby trajectory. So the presence of at least one positive Lyapunov exponent is one of the ingredients of a chaotic system. We will see later in the presentation what is the other ingredient that we will touch also in this presentation. And so if we have a big capital N degrees of freedom, let's assume we have small n positive Lyapunov exponents. So this small n defines the dimensionality of the unstable manifold of this system. So that is one of the measures of how unstable the system is. The second measure of how unstable the system is the size of the first Lyapunov exponents that has the most relevant role. I'm not going to go into details. And the third measure of how unstable a system is the Kolmogorov-Sinai entropy or metric entropy that defines, and this is, I'm using here the Pesin formula, Pesin identification, between the sum of the positive Lyapunov exponents and the metric entropy that defines how much information is generated per unit time by the model itself. And the positive Kolmogorov-Sinai entropy is also associated to chaos. So these are asymptotic, infinitesimally small. These objects are constructed by looking at infinitesimal small perturbation evolving on an infinitely long time, taking a limit. Of course, one can construct also local finite time equivalent of these objects. So one can study for a given initial position on the attractor of the system and defining a time scale t, one can find a spectrum of finite time Lyapunov exponents, can count how many of such Lyapunov exponents are positive, and define a local quantity that can be associated to the Kolmogorov-Sinai entropy. So the first one is an asymptotic. This is a local. The first set of quantities I indicated is asymptotic and is global. This set I'm talking about is local. So we will look at both of them. So the first result I want to mention has been obtained on a simple two-layer quasi-geostrophic model, indeed with Sebastian Schubert. So we have a simple two-layer model with a bump which represents orography. Orography is essential for catalyzing blocking events. And the presence, what we have discovered that this simple model is turbulent, has blockings. And indeed, we have discovered that if we take a conditional value of, as an example, of the Lyapunov exponents with respect to the days when blocking is present, we discover that on the average, the atmosphere is more unstable than typical conditions. So the presence of blocking is associated to higher instability of the atmosphere. Now the question, so this was the first result we obtained, and now we will see that we can build a lot on top of this. This result was encouraging because the idea that blocking is associated with more unstable conditions than usual was confirmed on actual atmospheric data by a totally different approach used based on the use of study of recurrence of atmospheric patterns and extreme value theory by Faranda and others. So after this, we got convinced that it was worth investigating the dynamical causes behind such anomalous instability during the blocking. So we, as a first summary, as I said, blocking, the presence of blocking comes together with typically with higher instability of the atmosphere and enhanced baroclinic and barotropic conversion. Okay, so now we will look next step into the specifics of the process of onset and decay of the blocking events. And to do this, we needed we moved slightly higher in the hierarchy of atmospheric models. So we took a 3-layer, I mean, extremely well-known 3-layer model of the northern atmosphere, the northern hemisphere, proposed by Marshall and Montaigne in the early 90s. And this model has the incredible, it's a quasi-geostrophic model that is tailored in such a way to provide a really good representation of the mean state of the climate, and is well known to have an extremely efficient representation of the mid-latitude atmospheric variability as well, and has been widely studied for theoretical study on synoptic and planetary waves. So I just flash this slide that shows that this model, despite this incredible simplicity, I'm talking about a 500 degrees of freedom model to represent a northern mid-latitude, is able to represent in fairly well the variability of the atmosphere in the mid-latitudes. So here we will be talking about typically winter conditions. So on the first row, you have the statistics of atmospheric variability from EC and WF. On the second row, on the same scale, the statistics of the variability by this model. Very simple model, but yet a model which has, out of 500 degrees of freedom, it has 37 positive Lyapunov exponent and the Kaplan-York dimension that of the attractor of 89. So this is a system with very high dimensional chaos, very well developed turbulence, cyclones, and variability on very, let's say, developed quasi-geostrophic turbulence. So now we have, we take this model, we take a long run, and we study whether blocking take place. And of course, this is the starting point, and blockings do take place fairly, with a fairly, not, I wouldn't call it realistic, but reasonable prevalence in terms of percentage of days that are blocked, and the location of the blocking is perfectly well captured. 0 is, of course, in the longitudes, is near the Atlantic Ocean, and 180, of course, degrees is the Pacific Ocean. So I would say that this model is, of course, not realistic, but is in some sense Earth-like. So the first so these are the asymptotic results. So now let's look at the fluctuations, because we want to see how diverse is the attractor of the system. So the first very interesting result that I was quite, I mean, that shocked me a bit, was that this system has, on the time scale of 1 day, which is short but not so short, a huge variability in the 3 main dynamical indicators of instability I mentioned before. So the first Lyapunov exponent fluctuates wildly. The Kolmogorov-Sinai entropy, the local version of the Kolmogorov-Sinai entropy, fluctuates wildly, and the number of unstable direction also fluctuates wildly. So just referring to the last one, we have a fluctuation between, say, 20 and 60. So different regions of the atmosphere can be very diverse in terms of instability and predictability. And this actually fits very well with a well-known fact in meteorology, that predictability is extremely state-dependent. But here we can quantify how much this is the case. Now, next step has been the following. Now, assume we collect all days when we have Atlantic blocking, and then we divide the blockings according to their length, say 3 days, 5 days, 7 days, 10 days. Now we choose as, we stratify all the results according to the length of the blockings, and we set as day 5 the onset of the blocking, and we plot on the y-axis the number of locally unstable dimensions. What we obtain is that, in the case of Atlantic blocking, first, the longer is the blocking, the more unstable are the corresponding conditions of the atmosphere. Second, the instability peaks at the onset of the blocking and at the day the decay begins. So one can, in a very unwavering way, interpret this as the fact that the system, in a thermodynamical sense, feels the cost in terms of production of information of creating the coherent structure that constitutes the blocking. Okay, so creating this organized structure, this object that stays there, that looks like a very special deviation, something that's very non-typical, requires a lot of instability and will be energetically expensive and will be extremely expensive in terms of entropy production as well. This is the Pacific blocking. In the case of that was the Atlantic blocking. In the case of Pacific blocking, things are partly different. So it is still true that the longer the blocking, the higher the instability. But in the case of the Pacific blocking, the instability peaks in the second half of the life cycle of the blocking itself. And this already shows a fundamental difference between the two blockings. So the Pacific and Atlantic blockings are two different beasts. And in fact, this is well known from meteorological literature as well. Now, a nice meteorological input, we're always trying to somehow go to the very fine path between geosciences and mathematics, is that if we construct one of the most relevant teleconnection pattern of the Northern Hemisphere, the Pacific North American PNA pattern, we observe that the negative phase of the Pacific North American pattern, which corresponds to positive in this graph, because this is an index of an empirical orthogonal function, is associated with the high instability. And it's also associated with the presence of a large-scale deviation from the zonal flow. So we sort of closing the circle between the classical meteorological understanding of a large deviation from the zonal flow and the characterization of blockings through the tangent in the tangent space. Okay. So concluding, we have learned something about the process of onset and decay of the blockings, and we have understood that longer blockings are associated with higher instability, and they are also rarer. Is this by chance? Okay. Now, the question, we're coming to the end, and now the question is, what is a blocking? I mean, is there something special about these blockings, or are these just large deviations, but they don't have any color in it? So can we paint the blockings as blue? I don't know, compared to other fluctuations which are in gray of the atmosphere. Is there something special about that? Now, to do this, we have to resort to a totally different kind of mathematics. So we have to consider the theory of unstable periodic orbits. So if we look at a chaotic system, we can take a totally dual viewpoint with respect to the usual one. The usual one, goes like this. I have a chaotic system. I start from an initial condition. My orbit will populate an attractor, and the first Lyapunov exponent and the spectrum of Lyapunov exponents will describe the divergence of the trajectory and the convergence along the dissipative part of the flow. This is one way to see it. That's the way we do a numerical integration, but there is the dual way. The dual way is the following, that is the strange attractor of a chaotic system is densely populated by unstable periodic orbit. So there are islets of order amidst chaos. These are closed trajectories, so these are true periodic orbits, but unfortunately they are unstable because the system is chaotic. So you can see the chaotic orbit as the result of being repelled between all these UPOs. So it's a result of a continuous repulsion. Okay, you have this UPOs that push trajectory away, but you're pushed away from one trajectory, then you hit another one, and then you're pushed away. Of course, it's very hard to find these trajectories, but there are algorithms that help us do that. So in some sense, actually not in some sense, quite rigorously, each UPO is a natural mode. It's a true nonlinear solution of our problem. And one can compute averages of observables through a weighted average of the value of the observable through this in each of these UPO. And these are the so-called trace formulas. So one can classify UPOs according to their period and their instability and construct the expectation value of any observable phi rather than through the typical ergodic average or the time average using ergodic assumption through such a special, difficult, complex, convolute averaging, which is though extremely elegant from a theoretical point of view. Now, keep in mind that longer UPOs are less populated because it's very hard to stay a long time near a repelling trajectory. And a more unstable UPO tends to be less populated because it has a higher power of repelling trajectories. So the second element will be essential for us. Now, just to give an example of how things work, this is a video produced by Chiara Aiocchi, and in this video we show a trajectory of Lorentz 63, and at each instant we are plotting the UPO that is closest to the orbit itself. So you see that somehow the trajectory follows for different length of time a UPO and then jumps to the neighborhood and another UPO. Now, this seems hopeless. How you can find UPOs in 500-dimensional space? And it's impossible. That was for a long time my belief. Indeed, these methods have proved a huge efficacy in studying turbulent flows. And there was a few years ago a special issue of Journal of Fluid Mechanics where it was shown how to use UPOs to understand turbulence. Now, can we bring this to the, in fact, more complex world of atmospheric dynamics? Can we use this to understand blockings? And my answer is yes. So we found, and Andrei Gritzon is mainly, of course, to be the person who did most of the job here. We found about 2,600 unstable periodic orbits in this 500-dimensional space. And these orbits are very different in terms of period and instability. How different? Well, another thing first I want to say that we have among these orbits which have zonal flow, orbits that fluctuate between zonal flow and blocking, and orbits that have blocking events. And in fact, the blocking events we get in this simple, relatively small sample of UPOs are exactly in the right position, where we get blockings in the original trajectory. So the result is these UPOs are incredibly heterogeneous in terms of their dynamical characteristics. So some UPOs are much more unstable than others. So this shows that the system is, mathematically and rigorously shows that the attractor is extremely heterogeneous. And in fact, the fact that we have UPOs with different number of unstable directions is a proof of the fact that this attractor is non-hyperbolic. And this will be essential for the last comment I will do. What's the relevance of blockings in this? So the very fascinating result I fancy the most, is that UPOs featuring blocking events are much more unstable than typical UPOs. So now we understand that blocking events are something very real in the sense that they exist as parts of the trajectory in the neighborhood of a special bunch of UPOs that are very unstable. So so these special UPOs with higher instability support the possibility of existence of blocking events. So blockings are special. They are not just typical UPOs, they come in association with very special, very unstable UPOs. So they bias, in some sense, the statistics enormously. So we understand that if an orbit persists for a long time near one of these special UPOs, we'll have blocking events, and all its dynamical characteristics indicating instability will be biased towards higher instability. Okay, so these are the building blocks of the dynamics of the atmosphere, and we have seen that blockings are not just special visually, are special in terms of composition of these building blocks. So this is the main result of the paper of this study. And now we understand that the Markov chain models of the coarse-grained dynamics I discussed above can be interpreted as describing the transition of an orbit between different groups of UPOs. We paint blue the UPOs that correspond to a certain kind of blocking. We paint red the UPOs associated to the other kind of blocking, and we paint as pink the UPOs associated with zonal flow. And then we discovered that the transition that I showed before in this simple matrix have to do with the dynamical processes encoded by going from the neighborhood of a group of UPOs to the neighborhood of another group of UPOs. I mentioned non-hyperbolicity. So this system we have found, in fact, this is a quite rigorous result. It's enough to find two UPOs with a different number of unstable dimensions to say that the system is non-hyperbolic. Here the spectrum, the variability of the number of unstable dimensions is huge. What are the main implications of this? They are very important. First, these are general mathematical results. If a system has a variability in the number of unstable dimensions, then it's very hard for any numerical model to shadow this for a long time. And this, to me, is a good reason why it starts to predict with numerical weather forecast onset and decay of blocking events, which are mainly responsible for such a variability. Second, lack of hyperbolicity means lack of structural stability. Lack of structural stability means it's very hard to construct a model able to represent the statistics of the system. And second, if one thinks in terms of linear response theory, means that it's very hard to predict and represent how the system will respond to small perturbation. This last result, the variability in the number of unstable dimensions, is also very relevant for data assimilation. Why? Because some of the modern proposals for improving data assimilation are based on the idea of assimilating only in the unstable space. So we try to reduce the error only where errors grow. But as we have seen, there are huge portions, potentially huge portions of the attractor where error grow, of course not asymptotically, but on a finite time scale, also in what is asymptotically the stable manifold. So this explains why in the actual implementation of the algorithms of data assimilation in the unstable subspace, people need to add few extra directions and dimensions to accommodate for transient growth. And I think that we have explained here the reason why this is the case. So coming to the conclusions, so this has been a long and painful story, and it has taken, I would say, 4 years to get to learn a bit more. So the idea is blocking events are on one side very complex mathematically, on the other side they seem to be present even in much simpler systems than the atmosphere. So my take on this is that there is something fundamental about blockings. In order to understand them, we have to study the heterogeneity of the attractors of the atmosphere. Even in a simple model like a quasi-geostrophic model, such heterogeneity is very present. So understanding these properties is, very, I believe, very interesting on its own. On the other side, it's, I think, a necessary step if we want to improve structure, provide hints for structural improvement in state-of-the-art numerical weather prediction and climate models. Clearly, just incremental innovation based on increasing the resolution, slightly tuning parameterization, and so on is not going to solve the problem. This is a case, I believe, where some basic research is very important. What I've shown today is, of course, not so rigorous and in some sense not so elegant, but I believe shows that there is a huge potential for these tools and these ideas. Thank you very much.